Hello dear colleagues, I would like to present for you our paper entitled Available Bandwidth Guided On-Demand Distance Vector Protocol for FANET. All of us know that flying ad hoc networks suffer from packet loss due to nodes' high mobility and congestion. Our contribution is that we suggest a protocol that chooses neighbor nodes with the highest number of entries in their routing table to reduce the overhead that AODV protocol suffers from. However, this modification may lead to congestion. Therefore, we add available bandwidth estimation on the routes to overcome congestion. We called our protocol Available Bandwidth Guided On-Demand Distance Vector Protocol, ABODV. In this figure, we see a link breakage where neighbor nodes inform the requesting node about it using a routing error message. In this figure, we see the ABODV selective route discovery process. So the source node S sends requesting messages to its neighboring nodes, and only the nodes with the highest number of entries are chosen. Then the neighboring nodes which were chosen, they inform the requesting node using a reply message about the minimum cost routes which lead to destination. In this figure, we see ABODV protocol performance, and we see that there is an overhead reduction compared to AODV using our simulator. So the red line shows the reduction percentage of the overhead. As we mentioned at the beginning, we used an additional metric, which is the available bandwidth, to guide the routing and to overcome congestion and to balance the load over the routes. So for available bandwidth estimation, we used our simulator, which chooses probing trains of variable packet sizes and variable time interval as shown in this figure. And we see that the sizes of the packets are increasing and the time intervals are decreasing. And in next figure, we see the probing rate relation with the probing packets order. Here we see that we used n number of packets equal to 30, delta t equal to 0.5 milliseconds, delta p, the difference in size of the packets is 50 bytes. And using all this information, we calculated the minimum and maximum values of the available bandwidth range and the length of the probing train. In this figure, we see a test network composed of 6 coax Clover nodes, cross-traffic sender and receiver, probing packets sender and receiver, and 2 routing nodes or relay nodes. In this figure, we see the relation between the available bandwidth in megabits per second and the cross-traffic measured in megabits per second. In this figure, we see the available bandwidth relation with the packet loss. So the percentage of packet loss relative to the available bandwidth, estimated available bandwidth in megabits per second. When we talk about overhead reduction, overhead is as we all know, is the number of hops that props traverse. So to reduce the overhead, we use two techniques, either one of them. Prop pruning. Here, if there is no satisfactory bandwidth on path between node pairs, the prop is pruned. In prop aggregation, when paths share a common portion, the prop is forwarded only once along this shared portion or shared path. In this figure, we see prop aggregation and prop pruning. So we see that ABODV routing overhead grows less than traditional routing. So for example, for a delay threshold equal to 4, the overhead decreased to here the red line to 98% in the case of pruning, and to on the green line to around 78%. As a conclusion, in this work, ABODV protocol was introduced and its core architecture was described, and it was found that it performs better in the networks with dynamic traffic and is more scalable than AODV. Estimating the available bandwidth offers us the ability to overcome congestion and to achieve load balance over the network paths. Thank you for your attention, and I'm ready for your questions.